Okay, so we continue from the point where I stopped yesterday. So yesterday, last thing I did was to discuss the analytic properties in general of this matrix. And so this somehow gave you the idea of how we describe a field theory in the language of particles. But of course, the field theory contains also the fields. And so I now briefly conclude on this, explaining how we get in touch with the fields in the particle formalism. So first of all, the Hamiltonian momentum that we introduced yesterday act as generators of translations in time and space in such a way that we will, this is the Hamiltonian. We will regularly use this to extract the coordinate dependence of a field in this way. Then, so these fields in the basis of particle states will be characterized by their matrix elements on this basis. And in particular, we introduce the so-called form factors, which are nothing else than, so I use the notation Fn phi P1 Pn. These are the matrix element between the vacuum for the operators in 0 and the n particle state. Okay. In terms of this, we can write a correlation function. Excuse me, what do you ask? X1, x2 are our coordinates in a Euclidean space. So x is equal x1, x2. So these are the coordinates I introduced yesterday. So the notations are the same. And x2, you remember, is imaginary time. So I was saying now we can, using this matrix element, we can expand. So this correlator becomes the expectation value on the vacuum of the product of the fields. And we can introduce in between the two fields here a complete set of states. Let me use this short notation for n particle state. So these n particle states are this one here. And so this becomes 1 over n factorial sum n from 0 to infinity the P1 2 pi a 2 pi E1 the Pn 2 pi En F. Excuse me, of course. Phi P1 Pn e to the minus the distance sum over times the total energy equal in writing this, I'm considering phi a scalar operator, so rotation invariant. So I know that the correlation function will depend on the distance, and I can choose for the make the computation easily x equal 0, x2. I'm also using here, and I say this once for all, the normalization of the states in this form, 2 pi E1 delta P1 minus P2. Okay, so I'm writing these things once forever. I will no longer repeat them in the future. And another observation here is about when this distance between the points become large, you see that this sum will be dominated by the states with the lowest energy, which means by the states with a small, minimal number of particles. In particular, the leading decay at large distance will come from the one particle state, n equal 1. And will be dominated by the minimal energy of the particle, which is its mass, from which we see that the mass is the inverse of the correlation length we defined yesterday, proportional to the inverse of the correlation length. Last definition, we say that a field phi creates a particle if it's one particle form factor phi, so on the one particle state is non-zero. So this means that phi acting on the vacuum creates, in particular, one particle state which has non-zero overlap. Okay, that's enough for the definitions on this very general part. And now we move. So we want, first of all, to characterize critical points according to the philosophy we used yesterday, to get in touch with critical properties, universal properties of statistical models. So we start discussing now some general features of scale invariant theories in 2 dimensions. Since at criticality we have scale invariance. So as you have seen already several times, the simplest thing and the most convenient thing to do, first of all, is to introduce the complex coordinates z1 equal x1 plus I x2 and z bar, z and z bar x1 minus I x2. So this make easy, in particular, rotations. So if this is z, I do a rotation by an angle alpha. This takes a phase, goes into the alpha z. Z bar. Then when we go to fields, so a field phi of x is characterized by the scaling dimension x phi that we introduced yesterday, but also in general now I will consider fields also which are not scalar, but so in general there will be what I call the Euclidean spin of the field S phi, such that when I do this rotation by the angle alpha, the field takes the phase e to the minus I S phi alpha. Okay, so with this we can easily move to write the OP that Caroline mentioned a few minutes ago. So this is operator product expansion, is an important property of field theory. It says the following. So if I take a product of two fields, I can expand this on a basis of the fields. So here we'll have some new fields k and 0. And then here there will be, of course, the dependence on the coordinates. And of course, the two, the left-hand side, the right-hand side, we have to be such that the total scaling dimensions and the total spin rotational properties are preserved. And this prescribes, if you just think for a second, this form. So these are constants, structure constants, and then you have this scaling dimension k x I minus x j over 2, and then z over z bar sk minus si minus sj. Of course, I'm using the notation x k equal x phi k. Okay, so this follows easily from keeping dimensions and spins. And this can be written in a more convenient form as provided we define this delta and delta bar as follows. So the scaling dimension is the sum of these so-called right and left dimensions, or conformal dimensions, as we are going to call them in a second, and the spin is the difference. Okay. With this we can introduce a notion which plays somehow a relevant role in two-dimensional field theory, which is the notion of mutual locality. We say that the two fields, phi I and phi j, are mutually local if the correlation functions which contain them are single valued under a 2-pi rotation. So, which means z going to z e to the 2i pi z and z bar e to the minus 2i pi z bar. Of course, you understand this mutual locality is a property you like to have for a physical correlation function. It means that if I take this point around this other one and I go back to the same position, I find the same value for the correlator. Now, if we look at the OPE, we see that this statement amounts to say that, so namely, this mutual locality is satisfied if, look here, this gives nothing under this continuation because it is just the distance. So everything is determined by this term. So in the condition is that sk minus si minus sj is an integer for any k appearing in the OP. So please keep in mind this condition for mutual locality because we will invoke it repeatedly. Then let me introduce another guy that you saw several times in these days. So the energy momentum tensor T mu nu, which is a field of the theory, such that, as usual, the Hamiltonian is the integral of the space coordinate of the component, time component. The momentum is the integral of time space component. So this is a way to see that, in particular, this T mu nu has scaling dimension 2 in 2 dimensions. Then this is a symmetric tensor. And it is conserved, of course. These conservation equations can be written as d bar t equal d theta and d t bar equal d bar theta, provided we switch to these components t, which is so going to complex coordinates, this zz, and has dimensions. This is 2, 0. T bar is t, z bar, with dimension 0, 2. And theta is, well, in these notations, is minus t, z bar, with dimensions 1, 1. Okay, this is in general, but at criticality, so in a scale invariant theory, The fact that we have a 0 here means that t is actually a function of z only. T bar is a function of z bar only. And so this means from this equation that theta is a constant. But this theta has dimensions, and we have no dimensionful parameter in a scale invariant theory, so is actually this theta is actually 0 at criticality. By the way, theta is in the component x1, x2 is the trace of the energy momentum tensor. So the tensor is traceless at criticality. Now, let's make a first use of this property of mutual locality. We want our fields to be local with respect to T mu nu. So fields local with respect to. So this implies that if I take T of Z with some field phi, the OPE, due to the condition of mutual locality, this will expand will produce here fields whose dimension differ by an integer from the dimension of the field phi. This just go back to the condition of locality. I call these fields ln phi of 0. And then to match the dimensions, so the expansion is all in z, I have only z here, so I have to put here z to the minus 2 minus n. Where this ln phi has dimensions that you can read off from this equation. This is delta phi minus n delta phi. Of course, you have seen already this notation, this ln. It is not accidental. The point is that it can be shown, just looking more carefully to the properties of the energy momentum tensor, that in the field theories we are considering, these Euclidean field theories, scale invariance actually implies invariance under a larger group of transformations, which are implies invariance under transformations such that the infinitesimal matrix distance element changes in a multiplicative way, where this rescaling factor depends on the point. Yeah. Right. Thank you. Thank you very much. So, for alpha constant, this is just a global scale transformation, but here we have alpha that depends on the point, and these are the transformations which have this property are called conformal transformations, or the coordinates. Now, the peculiarity of the two-dimensional case is that any delta z equal epsilon of z, where epsilon is any analytic function of z, and similarly delta z bar equal epsilon bar of z bar. So for any epsilon and epsilon bar analytic functions, this property will be satisfied. And this is why, so the conformal group, the group of conformal transformations in two dimensions is infinite dimensional, which is the key point behind solvability of field theories in two dimensions. So infinite dimensional group. And this infinite dimensional character of the group, as you already have seen several times, is encoded into an algebra satisfied by this operators Ln, which is called the Virasoro algebra. What you see in the algebra, one of the things you see is this number C here, which is called central charge, and which is characteristic of the theory, and can also be shown to be, in a loose sense, proportional to the number of degrees of freedom of your theory. So it grows with the number of degrees of freedom, in such a way that we can say that this number for this in universality class will be smaller than the number for the three-state Potts model universality class, and this in turn will be smaller than the central charge for the XY universality class. XY was O2 symmetry, I remind you. Now, concerning this Ln, you see this Ln, they shift by minus n the dimension of the field. One can see that L0 has eigenvalue precisely delta phi when acting on a field phi. So it's generator of global scale transformation, while clearly L minus 1 is just the derivative. Well, I didn't say, maybe it's useful to say that I'm using these notations. Okay. Let me also mention that the consequence of the algebra that can be worked out is that the central charge appears in the OP of the energy momentum tensor with itself in the form C over 2z to the power 4 plus other terms. While if I take Tz with phi, this is a consequence of what I wrote before, will contain the term delta phi over z square phi of 0 plus other stuff. Okay, sorry. Well, now you see the point is that due to this underlying algebraic structure here, satisfied by these generators of the conformal transformations, the structure of the space of fields in this theory becomes, to a good extent, determined by the representation theory of this algebra. So somehow it's mapped into an algebraic problem. And I just tell you what's the main structure. So we can put here. So this ln shift play the role of shifting operators for the fields, for the scaling dimension of the fields, in such a way that the lowest weight representations of this algebra will correspond to family of fields in which we have a field with a minimal dimension, which is called primary. And then you start moving up in the space using the ln with n negative. So you move by one step using L minus 1 phi, which is the derivative of phi. By two steps, now you can do L minus 1 square, L minus 2, and so on and so forth. You generate in this way a tower of states in which the number of fields you have is determined by the number of partitions you can do of this total number L, which is called the level, into integers. And so this is called the primary. These fields that you generate in this way are called the descendants. And I will denote by this way the family of fields consisting of the primary and all the descendants. Now, there is a notion here in this representation theory which plays, in the end, a very important role in practice, which is the following. When you study representations like this, it can happen that you find a representation which is reducible in the language of such a kind of algebras. This means that at some level L0, you find inside this representation another one. Okay, starting with some field phi 0, which acts as a primary for a new representation contained into this one. Now, the technique here is that you can make this representation irreducible, factoring out this piece. And when you do this procedure, the representation you get, so in particular you see that you will get a representation in which now the number of states starting from this level is lower than the generic case. So the irreducible representation you get after this procedure is called a degenerate representation. So this gives a so-called degenerate representation of the algebra. And the primary here, yeah. Excuse me? You get the irreducible representation factoring out this piece, which essentially means that you set this to 0. This is called, in the representation theory, is called the null vector. So this kills all, this field and all the descendants. And so the primary here obtained after this procedure is called the degenerate primary. So phi, in this case, is called the degenerate primary. Okay, so I say this now because I will mention these degenerate primaries later on. Okay, so these are general features of two-dimensional conformal field theories. Now, what I want to do next is to look into the space of these theories, looking for the universality classes we introduced yesterday. So things like the easy model, the Potts model, the ON model. They must be inside here at some point, some place. There must be specific values of central charge for them, specific values of the scaling dimensions, and we want to understand what they are. So it turns out that actually to study these main universality classes I introduced is sufficient to work in the space of CFTs with C central charge up to 1. So for doing this, I start from the simplest theory you all know, which is a free boson with an action which I call H0, which is just the usual one. So phi is a scalar field, and such an action corresponds to an equation of motion. So this is free theory, so equation of motion makes sense. Also, in the quantum field theory, and takes this form, which is consistent with the decomposition of the field into chiral parts, depending. So I call chiral a field which has one of the two dimensions, delta bar, which is 0. So this satisfies the equation, and also everything is consistent with the fact that the correlation function phi of x, phi of 0. Well, you see, from here phi has dimension 0. So it's not actually a good scaling fields that we saw yesterday, which have power law correlations. Due to this dimension 0, this will have actually a logarithmic correlation, which in my normalization takes this form and can be written also as -1/2 z plus bar. And so this is the contribution of chi, and this is the contribution of chi bar. Now we can also write the energy momentum tensor for this theory, which in its most general form takes this expression. Where you see here there is a parameter q, which is not in the action here. But it can be, you can use the equation of motion to show that this implies that also for q different from 0, you have the conservation of t, so t conserved, and also energy and momentum are q independent. So this q actually is somehow an hidden parameter, an hidden degrees of freedom of this theory, which doesn't change the main properties like energy, momentum, or conservation. But such a modification of T has non-trivial consequences on central charge and scaling dimensions on the fields, because we saw that these quantities appear in OPs or involving T. And in particular, so you can go to those OPs. So you can consider T. You look at the term C over Z to the fourth. So this is a computation you can do by Wick theorem, the famous Wick theorem already invoked several times, just because this is a free field theory. And so it's not a difficult exercise to see that what you get is this result for the central charge. Then we said that this phi is not a good scaling field also because of these logarithmic correlations. To get good scaling fields, we take the exponential. So we introduce these vertex operators that Karelian has mentioned a few minutes ago. My definition, my notations is the following. For the chiral part, you have also, of course, a part in Z bar that you can define in a similar way in terms of chi bar. And now, if you look at the OPE T with such a field, the term producing again the field, this will contain the scaling dimension here. And you can read off. So I use this notation. This is the scaling dimension of the vertex operator. I call it delta P, and the result for this is this. So a generic primary, of course, will have both the Z and Z bar components in this form. With dimensions delta P delta T bar, given by this formula. Okay, so now we got to examine the consequences of this. Before doing that, just let me add another thing. So we say that we want the fields to be local with respect to with T mu nu. Now, we saw that T mu nu in general is the components T bar, but also theta. This theta is 0 at criticality, but it will become non-zero when we move away from criticality. And in particular, this will be proportional to the term that breaks scale invariance. So the term which drives us away from the critical point. And we saw yesterday that this term is something we write as coupling tau times the energy density field. So, in the game we play now, we will ask, according to locality with the energy momentum tensor, we will ask in particular locality of the fields with respect to the energy density. Right. With this we can move on, starting with the case of central charge equal 1. Which means Q 0. So this is the totally standard theory of a Gaussian field, in which this was written also by Cappelli. The OP takes this form. From now on, I write the OPs without all the coordinates because we know what they are. So we just need to know which fields are produced on the right-hand side. And through this notation, I mean that I will generate the primary and also its descendants in general. Now we can check under which condition two fields are mutually local. So we know the definition of mutual locality, we know the OP, which is what we need to do this, and you can check that this implies that, requires that twice P1, P2, yes, minus P1 bar, P2 bar is an integer. So this is general condition mutual locality for two fields. And now the next thing we need is to say, to identify an energy density field in this theory. Well, in general, this will be, has to be a scalar field, and we want it real. And a generic choice will be of this form, V bar plus V minus B, V minus B bar, which you can write as cosine 2B phi. With dimensions delta epsilon equal delta bar epsilon equal b squared, which comes from here with q equals 0. Then we look at the condition for locality of a field with respect such an energy density, and you just read off from here. This will be, the condition will be p minus p bar, well, this is not needed, equal m over 2b, where m is an integer. So all the fields we will consider need to satisfy this condition. And it follows from what I say that they will be scalar only if m is equal to 0. Otherwise, they have some spin. In particular, if we take m equal 1, we can write the following field. I call it capital psi. It has two components, psi and psi bar. Which are done like this. And then V1 over V minus V over 2 V bar. So this object has m equal 1, and also if you check the spin, so this has a spin as psi, well, let me write it, yeah, which is minus the spin of this other guy, psi bar. So I'm checking the spin on these two. This is 1/2. So this object is a complex fermion. Due to this half-integer spin, is the fundamental complex fermion, so complex, or as it is called, Dirac fermion. That you can build from the original bosonic field. Starting from this complex fermion, you can define, of course, two real fermions. This psi1 and psi2. So these are real fermions, also called Majorana fermions. And each of them, again, has two components. So psi equal psi comma psi bar. Now, one thing you see is that if v square is equal 1/2, you just put this here, you get that delta bar psi is 0, which means that delta bar of the derivative of psi with respect to z bar is 0. And this is the equation of motion of a free fermion. So at b square equal 1/2, we have free fermions. On the other hand, if beta square is not 1/2, this is no longer true, and these fermions will be interacting. In such a way, so we see that inside this theory we can construct these fermions, and we can think then of a fermionic representation of this theory. Namely, we can rewrite the same action I had at the beginning, A0 for the scalar field, in a fermionic form. I do it with the scalar, with the real fermions, psi. So this is the usual piece for non-interacting fermions. So it will correspond to b square equal 1/2. But then we have, in general, for other values of b square, some coupling, which will be a function of b square, and then an interaction in the four fermion form. So the property here is that g of b square of 1/2 is 0 to recover the free fermions. So the possibility of rewriting the action in this fermionic form goes under the name of fermionization, and if you do the inverse procedure, you are doing bosonization, and within this, the energy density, which was cosine to b phi, is related to the mass term for these fermions. Which has this form, is the usual bilinear of the fermions. Another thing we can observe now, since these are fermions, they have the property, the usual property that psi square is equal psi bar square is equal to 0. So in such a way that we can rewrite the four fermion interaction as some psi bar squared. So with this, you see that this action actually becomes invariant under rotations of the vector psi1, psi2. So these are two rotations for these real Majorana fermions become U1 rotations for the Dirac fermion. And M, so the integer which appears in the quantization of P minus P bar, plays the role of this U1 charge. So there is a O2 or U1 invariance in this model, in this theory, and we can look for a field which will play the role of the order parameter for this symmetry. This has to be a scalar field, and it has, with the definition of order parameter we gave, and it has to be charged with respect to this symmetry with the smallest charge, which is m equal plus or minus 1. So we take m equal plus or minus 1, and we ask this to be scalar field. If you put this together, you get these two components, which I call them sigma plus or minus, which are done in this way, and from which we read off the scaling dimension of this order parameter, which is 1 over 16 b squared. From the general formula for the scaling dimensions. Now, of course, so we have what we wanted, the dimensions of the order parameter and the dimension of the energy density. As a last remark about this, let me add that, of course, once we find this O2 symmetry, what we have in mind is that this is going to describe the universality class of the XY model. So we have O2. This leads us to XY, universality class. Now in the XY model, we wrote yesterday, the only parameter we had was the temperature, or J over T. Now in this theory we have a parameter which is B. So if we try to match the parameter, if we say that these are related, so if we say that B is actually a function of temperature, so it corresponds to temperature of the lattice model, well, then we reach the conclusion that we can change the temperature keeping a scale invariance, because changing this B, the theory here remains scale invariant. But this somehow seems inconsistent with what we said yesterday, that we have a scale invariance at a single point, Tc. So you may say, well, this means that this must be wrong. But actually, the story is more subtle. This is right, actually. And the way out of the paradox is that one can show in general that continuous symmetries, like O2, in 2 dimensions, do not break spontaneously. So I've not shown that continuous symmetry do not break spontaneously in two dimensions, but I hope I gave you an idea of what is going on behind this. Okay, so now I think we should stop for the break. All right. So we got in touch with XY. Another thing we can do is to look for now to comment about the Ising model. Well, you know, the Ising model is as a lattice model is the first one which has been solved among the models which have a phase transition, continuous phase transition. This was done by Onzager in the 40s. And since then, since the 40s at least, it is known that it admits a representation in terms of free fermions. So the Ising model, in particular, the Ising model is the theory of a single real fermion, one. Now, if we go back to our fermionic action here at 0, and we go to b squared equal 1/2, what we have, they're just two real fermions decoupled. So this means that for b squared equal 1/2, this theory describes two decoupled Ising models in the scaling limit. I've been told that I'm going too fast, so please interrupt me if you have questions. So, I hope it's clear. So Ising is one real fermion. We know this. I'm not showing it, but we know. I'm invoking the original lattice results. So b squared equal 1/2. These are two Ising models decoupled, and then from this we can infer that the Ising model has c equal 1/2. Because two copies will build the C equal 1 we were dealing with there. Then concerning the dimension of the energy density, it will be the dimensions, you see. Now these two pieces here are the dimensions of are the sum of the energy densities, epsilon 1 and epsilon 2, of the two copies of this Ising model. So this will be the dimension of this field computed at b squared equal 1/2, which is the decoupling point. So it was the dimension in general was for epsilon was b squared, at b squared equal 1/2. This is 1/2. Well, for sigma, the story is more subtle. Well, I have identified the sigma for the O2 symmetry. It is here. This is 1/16 beta square. So for beta square 1/2, you get 1/8. But this 1/8 actually turns out to be the dimension of the product of the two Ising spins. So this is 1/8, which means the delta sigma in Ising is 1/16. Half of this. Okay, so these are the basic information about the Ising universality class that I quickly mention at this point. As a last notion, in this C equal 1 case, let me look for the fundamental chiral fields. So I will erase this. So now I go back to the general theory C equal 1 with this parameter B. and I look for fundamental. Fundamental means they have, since they are chiral, they must be, they have a spin, so they have the integer m appearing in p minus p bar has to be non-zero, and fundamental means that it takes the minimal value, plus or minus 1. So minimal charge. So these are the fundamental chiral fields, and I call them eta and eta bar. And actually, due to this plus or minus here, if you just look at all the quantization conditions we wrote, this is eta plus or minus is v plus or minus 1 over 2b, and eta bar plus or minus v bar plus or minus 1 over 2b. In such a way that, well, their dimension is just 1 over 4 beta squared. Okay, so I note this here, and I will use them later. And with this, I close this synthetic discussion of C=1 conformal field theory, in which I just tried to underline some things that I will use later on. And what I do next is to move to the case C smaller than 1, which means now Q, so the parameter Q we had in the stress tensor of the bosonic theory, Q is real. Now here I will do an exercise of rewriting things that can look a bit crazy at first, but I will show you why it is useful in the end. So first of all, I rename this Q 1 over beta minus beta. So beta is a new parameter which plays the role of Q, which in turn I write in terms of another parameter which I call T in this way. So T is a parameter, nothing to do with time. Now if you do this, you can check that you can rewrite the central charge, which it was 1 minus 6 q squared, it becomes 1 minus 6 t plus 1. Then continuing with these redefinitions, I define these fields phi nu of Z. These are just the vertex fields with index p nu, where this p nu is mu and nu here are just real numbers. So this is defined as 1/2 1 minus mu over beta minus 1 minus nu over beta. So in terms of this reparametrization, I can write now the dimension of these fields phi mu nu, for which I will use a short notation delta mu nu. So this is t plus 1 mu minus t nu square minus 1. This comes from the original formula that Vp has dimension p times q minus p. So just reparameterizing everything, you get this, and in the denominator you have 4t times t plus 1. So why this is the exercise is worth doing? This is just because with this notation now, it happens that these fields, more precisely the fields phi m n with m n integers. So I'm taking these fields here. Mu and nu in general are real parameters. Now I take them integers, positive integers. These happen to be precisely the degenerate primaries of C less than 1 conformal field theories. So are the Of course, I'm not proving this. This is the result that you study the representations of Virasoro algebra for C smaller than 1. You find the reducible representation. You do the process of making them irreducible, getting these degenerate primaries. And if you do that, you get that they have these dimensions with the mu and nu positive integers. So I'm getting in touch with what I said before about the existence of these degenerate primaries, and I'm recovering them inside this discussion of conformal field theory within this original bosonic theory. Well, one thing I didn't say about these degenerate primaries is that they have as a consequence of the algebra and all that, they have a crucial property which is essential for most of the calculation you do with conformal field theory, namely that the correlators which contain such degenerate fields, they satisfy linear differential equations. Of course, I will not go into that, but I mention this just because the fact that they satisfy these differential equations allow you to put strong constraints actually to determine the OPE involving these fields, these degenerate primaries. Since the OPE is the tool that I use for my analysis, as I did before for the case S equal 1, I will write these OPEs involving these degenerate primaries just for completeness, in such a way that if you want to check what I'm going to say, in principle, you're able to do it. So this OPE as a consequence of these differential equations. So the OPE of a degenerate primary with a generic field takes this form, sum k 0 to n minus 1, sum l 0 to n minus 1. And what you produce is phi mu minus m plus 1 plus 2k. Nu minus n plus 1 plus 2l. On the other hand, if you take the OP of two degenerate primaries, so M1, M1, M2, M2, this expand as sum k from 0 to the minimum of M1, M2 minus 1, sum L from 0 to minimum of N1, N2 minus 1, phi. Okay, this is how they look like. And now with this, you can play the same game we played for sequel 1. I just list the steps of this game and the result. So first of all, you have to look to identify, to propose some energy density field. Now the energy density has the property that somehow has to be a fundamental field, which is invariant under the symmetry. And so in its OP, you expect something like identity plus epsilon plus fields with higher dimensions. So I mean that epsilon has to be the first field with excluded the identity appearing in such an OP. And this is something that we are able to do at present. We are not able to think of something like that unless epsilon is a degenerate primary itself. So I'm going essentially to assume, based on this loose reasoning, that epsilon is degenerate. So it's one of these fields. Then I look for theories which, when C equal 1/2, so which was the central charge of the Ising model, they reduce precisely to the Ising model. Namely, I want that delta epsilon is 1/2 at C equal 1/2. So I want to recover Ising as a particular case, when the central charge is 1/2. Now, if you put this into the formula for the scaling dimensions, you get two possibilities for epsilon. Either it is 1, 3, 1, 3, or 2, 1, 2, 1. So it's always a scalar field, so it is the same z and z bar parts. We have two possibilities for epsilon. Then we would like to look for sigma. Well, first of all, we look both for sigma and the fundamental chiral fields. So look for sigma and eta local with respect to epsilon. which is one of these two choices. And the locality will be determined by these OPs that you can use to analyze this condition. And then, as a last requirement, for sigma, we also require that in the OP you have this. Well, just because so epsilon will be neutral under the symmetry, sigma will carry a representation of the symmetry, so in the product it is quite natural that you find again sigma in the right-hand side, because it will have the right charge. Okay, so if you do this, you find, so according to these two possibilities for delta epsilon, in the case 2, 1, so in this case, you find that for delta eta, you find delta 1, 3, and for delta sigma, which is equal to delta bar sigma, you find delta 1/2, 0. For the other choice of epsilon, which is 1, 3, you find delta 2, 1 for eta. While here you get no information, actually. So you remain with a question mark there. To check this, you can use the fact that f mu nu is identified to f minus mu minus nu. This is a consequence of the formula for delta mu nu, which is invariant under this change of sign. And also the fact that we know that the chiral field for C equal 1/2, for the easy model, this is just the fermion, which has 1/2 as dimension. Okay, now in few words, these two solutions, you see, these are theories in which are defined for all values of central charge smaller than 1, and which at C equal 1/2 reduce to the easy model. According to what I said about the central charge, that it measures the number of degrees of freedom of the theory, it is quite obvious then to expect that these two solutions will correspond to, should correspond to the two models we saw yesterday, which had a continuous parameter inside, which was the Q-state Potts model, for which we could vary Q continuously. This will give some continuously varying central charge. And this model is a particular case. And the other case was the ON model, where again you can choose, you can change N and then the central charge continuously. And this model is a particular case. So we know we have those two models there, and we are finding that there are indeed two theories which can accommodate that. The point here is that in this kind of discussion you have no contact with the symmetry, you see. If you want to identify one of these with the Potts model, Q-state Potts model, where is Q? And if you want to identify the ON model, where is N? So we are going to look now to make contact with the symmetry, and so to do the precise identification, and then to determine the critical exponents of Potts and ON, and in particular in the limiting cases we saw yesterday of percolation and self-avoiding polymer. going back to the particle language, because there, in the particle language, we have a natural way of making contact with the symmetry. Okay. So this is what I'm going to move to now. Yeah, if you have questions, please. Well, this is based on symmetry. I said I don't see the symmetry, but I know that there will be some symmetry behind. And I know that the energy density is invariant, so it's charge 0 under this symmetry because it is part of the action when I go out of criticality. Well, sigma instead is the other parameter, is charged. So if you match the charges, so they match, and so in general this will be there, because it has the right symmetry to be there. Other questions? Yeah. Oh. Condition, which one? To identify these objects. I mean, you see, I explained, I argued that epsilon, I'm looking for epsilon. I explained that first of all, I expect that it is a degenerate field. So this reduces the investigation to these fields with these dimensions I had wrote for these fields with mn integers. And then I argue that since I want that at c equal 1 alpha, I want to recover this model, this gives me these two options. Okay. Then I moved to, I look for eta and sigma. And I want that they are local with respect to this. The locality I check using these OPs. I wrote them, they are very ugly, but I wrote them just because in principle you can do this exercise if you like. Checking what are the fields which are local with respect to these choices of epsilon. And I added some additional condition. For example, for eta, I know that must be the fundamental chiral field. For sigma, I added the condition on the OP, epsilon sigma, that should give back sigma. So for the first choice of epsilon, this actually identifies the order parameter, while for the second choice, it doesn't give information. Okay. We expect, yeah.
But so for n is smaller than 2, because we said that the xy model has central charge equal to 1, no?
Right.
So
yeah, you got the point. Yes, this is going to be the one model up to n equals 2 at most. Yeah, you are perfectly right. Yeah.
But you can only get consistency for certain values. You can't have a continuity variance of the chart.
Yes.
Because you were saying that we have those continuity variance of the chart aspects. So you are going to put this into as a requirement.
No, I expect, since yesterday I said that both Potts model and ON, they have this representation in which Q for Potts and N for the vector model, they can be taken continuous. Now, this Q and N, you understand, when I increase them, I increase the number of degrees of freedom of the model, because they are the number of states. And since the central charge is sensitive to this increase of degrees of freedom, so in those models, ON and Q-state Potts model, the central charge will increase with Q and N continuously. And these are the two theories at c less than 1, in which I have this property of a continuously varying central charge with the physical properties that I expect in order to describe the statistical models. Is okay? Okay, so as I said, what we miss in all this picture is the symmetry. And we now try to get in touch with the symmetry going back to particles. So what we want to do now is to deal with the particle description for a case where we are at criticality, so in a scale invariant situation. So we have to figure out what a meaning for a scale invariant scattering. So yesterday we saw general properties of scattering. So this should be a particular case of that. Which particular case? Well, first of all, scale invariance means there is no scale, no dimensionful parameter. This means that the particles cannot have a mass, because a mass would introduce such a scale. So we have massless particles. So their dispersion relation is a particular case of the one of yesterday with m equals 0. And this, as you understand, gives me two possibilities. So the energy is always positive, so I can have that the momentum is equal to the energy. And so this will be particles, so it's positive, they move toward the right, so I call them right movers. The other possibility is that P is minus the energy. So it is negative, so I call this left movers. Then if I think of fields which create these particles in the way I defined at the beginning, well, it is quite clear if you take this matrix element and you consider these conditions, you extract the x dependence, this is going to give a factor e exponential ipz for right movers and a factor a to the ipz bar for left movers, just because p is equal to e plus or minus e. So it is quite clear that these left and right movers will be naturally interpolated by chiral fields. And these chiral fields are the fundamental chiral fields I identified before, this eta. That's why I carried through this analysis. So here I associate eta, and here I associate eta bar as fields which creates the particles. Then, so the picture now we have for this scattering is the following. So we have a right mover and a left mover with momenta P1 and P2. So I repeat this right, left. So I don't consider the particle species for the time being. So let me think of the case there is just one species. So I don't have indices around for the time being. Now this, I look for the amplitude. So this will be some amplitude. So again, there are no indices. And Well, I have the following situation. So this will be some dimensionless quantity. In a theory where there are no dimensionful parameters, and in which the only relativistic invariant this object could depend on is the S we saw yesterday, square of the center of mass energy, which has dimensions. So this means that I cannot build any dimensionless quantity in this scale invariant theory, which has a dependence on S. So S is a constant. Doesn't depend on the momenta, P1 and P2. And in this case, without the indices, the unitarity tells me that actually, in this case, will be a phase. Now you see the fact that the scattering amplitude doesn't depend on the momenta can only mean that there is no real interaction in this situation. This, however, doesn't mean that S is 1 necessarily, because these particles move on a line. So when they scatter, they interchange their position. So somehow there is a notion here of a statistics for this particle related to the interchange of the position during the scattering process. So this is why this phase incorporates actually this notion of statistics and can be different from 1 depending on the statistics of the particles. So what we expect is that this will be 1 for bosons, -1 for fermions, and something else for objects which are not bosons or not fermions, and we could call parafermions. Now, next consideration related to the fact that there is no actual scattering, actual interaction, but only statistics. I can think of 2 ways of, so in my space-time, so this is my scattering process. I start with the particles in these 2 positions. I end with them interchanged in space. But since there is no real dynamical interaction, I can think to realize the same exchange of position by rotations of the particle here and here. This is also an exchange. But I know how to, this rotation by I pi are implemented. They will be determined by the spin of these fields which create the particles. So this pictorial equation translates into S, the scattering amplitude, equal to the total phase I get from this rotation by I pi, which is determined by the spin of eta minus the spin of eta bar, because I will have eta here and eta bar here. Now we know these spins because we know the delta and delta bar for these fields, and putting all together we get e to the minus 2 I pi delta eta. Which is an interesting equation because it relates a scattering amplitude, which is something which concerns particles, to a scaling dimension, which is something which concerns fields. So we get contact between these 2 objects quantitatively. And we can start then our analysis, but let me complete this first by saying the following. Now, first of all, since this is a particular case of what we saw yesterday, we can write, for this particular case, the equations of unitarity crossing that we had yesterday. And they will look like this. So for unitarity, this is just, you just take the formula of yesterday and use the fact that this, sorry, I didn't say one thing. Unitarity, as long as there are no indices for the particle species, just says that this is a phase. That's all. Now, in the general case, there will be indices. In the general case, I will have several species of particles. And then, in that case, I will have a unitarity equation which takes the more general form we saw yesterday, and which looks like this. I remind you, we had this pictorial representation for the unitarity equation A, B, E, F, C, D. So these are the two scattering points. Then we also have the crossing relation, that in this particularly simple case just says that SABCD will be equal to SD bar A, B bar C star. So, okay, these are the equations on which the game will rely. And I will also use this notation to encode the notion of this scattering between a right mover and left mover. Since they are associated to eta and eta bar, I will use this notation here. So I have some eta, this time with an index denoting the species in general. I take the scattering on right mover and left mover. This just means that I take them to scatter. After the scatter, they exchange their position, so I will have eta bar before eta. But in the scattering, they also get, they produce a scattering amplitude. And I have to consider, given this initial state, all the possible final states. And so this is something I codify, saying that I sum over the final particles with the amplitude S, A, B, C, D. And I have the right and left movers now exchanged in their position. Okay, so this is the general rules of the game that we will play tomorrow to solve the case of Q-state Potts model and ON vector model. We stop here, it's quite late. Any question? Well, there is no interaction. No, it's a good question, but indeed, since there is, I say, there is no real interaction, only statistics, there can, yeah, there can be no particle production. Okay, apparently it's fine. Thank you.